So, in the next, so we had the last session where we talked about the tips and tricks of Docker. So this time we have uh, another Docker captain who is a co-founder of a company named Topple, and which is based on Arizona. He is an author of a book called Docker in Action, and he is basically an experienced software engineer. He is a blogger. He's a people manager, published author. And in today's session, he is going to talk about the challenges, the cultural as well as the technical challenges around the monolithic to microservices. So, ladies and gentlemen, let's welcome Jeff Nikolov onto the stage.
Oh, 1 second. Hey, everybody. Nice, sleepy post-lunch session. There won't be any demos. I don't do post-lunch demos. I'm not going to tempt the demo gods that much. So, there's nothing to really follow along with. This is like almost a semi-cultural talk. A little bit more about myself. I've been in tech since the early 2000s, and before I left to co-found a company doing software engineering consulting and container consulting, I was working at Amazon, where my team of 8 owned something like 300 individual microservices. And I got to see all the pain associated with that. Got to really live high-pressure ops. In 2012, back when I was still an engineer, not that you ever stopped being an engineer, but I had a really interesting meeting with my skip report, who asked me a really simple question. He's like, do you understand how important your team of 8's components are to Amazon? And I thought that was kind of an interesting question, like how do you actually, what terms do you describe that in? Which is a totally separate interesting exercise, but he said, for every hour that any of your components are down, Amazon loses about $15 million. And so, and you just kind of just stopped there and like give you a second to let that sit in. And so when it comes to like building a microservice architecture, as I'm going to go over here, like it introduces a lot of logistical problems. There's a lot of moving parts that suddenly you have to account for. And dealing with high pressure operations, like, the difference between 15-minute root cause analysis and a 30-minute root cause analysis can mean literally millions of dollars, not just you being woken up at 2 a.m., right? It means real customer pain on a large scale. And so dealing with all those little pieces and orchestrating that delicate dance that make microservices work, it's really important. And it's really important to think about. And it's really important to try to grow into rather than taking on too much at once. So it's just after 2. I'm going to go ahead and get started. So I want to start first, why are we migrating from monoliths to microservices? The reasons kind of vary. Generally speaking, you're going to hear things like, our release engineering for our monolith is getting too slow, right? We've got 200 developers, they're all contributing to the same into the same code base, but in different pieces, and they're never ready at the same time, and which means our releases only go out very infrequently, and it's slowing us down as an organization. Or you might hear our monolith is built on 10-year-old technology, and while it still functions, it's very difficult for us to hire new talent that wants to work on that. And so changing technological context can make it is difficult to integrate into monoliths and can make it difficult to staff teams. Other reasons to move away from monoliths, you can have all sorts of side effects, leaky abstractions, you have resource isolation problems between different components in the same stack, and sometimes it takes a Herculean efforts to actually resolve all those things. In the case of, depending on when you started and when you're thinking about moving, your entire engineering philosophy may have shifted in that time. It could be very well that you started building your monolith when you were a team of 5, and you were okay skipping abstraction layers like coding to interface if you're in object-oriented land, and you're coded to implementation everywhere, and you've got poor unit test coverage. And so making any changes in your monolith become very, very expensive. And last but not least, maybe security. If you're running a monolith stack and someone compromises your one component, then they've compromised your entire platform. In a microservice architecture, it's much more easy to isolate and partition different processes because there are multiple processes. Just because I've popped my front end layer does not necessarily mean that someone has compromised my string tokenization layer. So there's a lot of reasons to migrate. I don't want to belabor all that. If you're in here, you're either thinking about it or you're already kind of going down that path. So there's really 3 things that I hope people learn. The first, how and why microservices end up following along organizational lines, how their architectures and the way that they communicate end up following those patterns, and why that's a good thing. How we can learn from monolithic tooling, from all the same tools that we have in monoliths, to inform the tooling we should be looking for in our microservice environments. Because, spoiler alert, they're almost identical. And lastly, how you can achieve operational excellence at scale by taking a logistical approach and using tools that help you think about the logistics. Because the main difference between monoliths and microservices are you've got a lot more of something, right? It's like dealing, I could be a package carrier if I only had to carry one envelope from point A to point B. There's a big difference between performing that action and holiday delivery for packages at Amazon, right? So the challenges in migration. Really, in owning service software, especially really any kind of software, you have the same set of challenges. You're building, shipping, and running your software. The big change is in context. And the context has changed in a couple really important ways. Microservices are distributed and independent. You have more and smaller focused components. You have components that have independent life cycles. There's a lot more entropy in your system. You have network versus memory component addressing, where everything before was a function call, which means a memory jump. Today, it's an actual network call, but it's still an addressing problem. You have distributed and localized state, meaning something that's written to disk over on this part of your system is not necessarily accessible from disk on this part of the system. You have unreliable wall clocks. If you have a microservice infrastructure, regardless of whether or not you think you have distributed systems problems, you have them. You can't trust your clocks. This comes out in a couple very specific ways. You have independent component runtime state. This means like health. It's no longer binary. You can't say, yeah, my service is up because you have 300 services, not one service. You have independent, which just means that you have way more failure modes than you could have ever had before. And then finally, you have independent component experiences. When I look at the state of the world from the perspective of one of your components, that component is directly consumed by and consumes some other set of components. And so it kind of gives you a very interesting top-down relationship and helps inform the way you should think about ops. So I'm going to start off kind of rolling back all that hyper-technical differences, and I want to talk a little bit about the culture. And this really comes down to silos and cognitive limits. Raise your hand if you've heard of Dunbar's number before. There's like 2 people. That's awesome. I found out about this 2 years ago. So there's a psychologist, some dude Dunbar. I'm going to do this a total train wreck of a job. But Dunbar's number is about 150. There's some disagreement about exactly what it is. 150 to 200, let's say. And what Dunbar's number describes is the number of stable relationships that you can maintain just with people was where Dunbar was coming from, because he was studying psychology and the nature of relationships. So he's basically saying that you can maintain these stable relationships with about 150 people. Relationships are particularly interesting because they're in constant flux, right? It takes a lot of effort to maintain a relationship. I generally have to kind of know what's going on over there. I have to know how I feel about you. I have to have some rough idea how you feel about me. I have to keep kind of in touch with what your relationships look like to make sure that my perspective of you shouldn't be changing. And interestingly enough, like that's actually, I think the human case is really a specialization of a generic or of a general phenomenon, which is like the relationships that we can have with things, with ideas, and like code. Code constantly changes. And we have a relationship with code. I've felt it. I've lived it. I know that this is the case. The next cognitive limitation, it comes down to Conway's law. Raise your hand if you've heard of Conway's law. This should be much more popular. All right, cool. So like 25 people. Conway was this guy, and he wrote a paper. And in it, he postulates that organizations that design systems are constrained to produce designs which are copies of the communication structures of those organizations. And there's a lot of reasons for this. You could conject about whether it's like reporting structures or goals or focuses, or like implicit contracts between different parts of an organization, different held domain knowledge, whether it's actually like who the people are in different parts of the organization. And sometimes it really does represent business units. So rather than kind of fight this, which I think a lot of people naturally try to fight it, even though they see it happening, they try to fight it, I'd actually recommend that you embrace it. Because it helps with a few things here. Specialization and interaction between components at this high level helps you build, it helps you focus your development efforts. It helps you build local domain knowledge. It helps you build out focused on-call rotations. A lot of our clients and systems that I've owned in the past that are monolithic in nature, you'll have like one team or a couple teams or an org that all own one monolith together, and they all have one on-call rotation, and there will be like 70 people in this on-call rotation, which just generally means that on-call rotation is crap. There's no way with 70 people in that rotation that you could ever get enough operational knowledge on this piece of software to be effective at on-call. Right? It's slow. There's no domain knowledge. You have no experience. Even if you've done it once, the next time you do it will be almost a year later. So what's the likelihood that code base is the same? What's the likelihood that you remember what you did a year ago? Hopefully, I mean, this is where teams break out the sledgehammer of like literally just, I don't know, reboot the server. Right? Which, it's okay. We can all say that that's our guilty, like, first step triage. But it lets us focus a lot more. It lets us build specialized on-call rotations and target failure. Integrate, wherever the interfaces come from, I'd love to build a system that helps us integrate on interfaces that are defined from somewhere. All this dependence on leaky abstractions and implementation is really unhealthy for a system. It makes things very difficult to maintain over time. It raises a lot of questions about who should be responsible for coming up with different designs or validating and reviewing certain designs going forward. And if you talk to business units, what the biggest problem is it comes down to who should pay for it. If you have one component or a couple of components that span business units, the water gets very, very muddied at the management layer, at the senior management layer, like who's going to put up the resources to make XYZ changes. When in an engineering perspective, it might be completely obvious what needs to happen. But at the end of the day, someone's got to pay for it. So embrace these kinds of things. It doesn't really matter where the interfaces come from, as long as you have them. And while we're speaking about interfaces, especially in microservice land, but also related to business units and organizational hierarchies. Like, when we talk about APIs, we say API, everyone in this room says API all the time. It's all about APIs, and APIs sounds like something you can version, and you certainly can, but especially in a microservices land, but also when you're talking about relationships between business units, oftentimes it's more important to talk about contracts, because it really is more about, okay, this is our agreed upon relationship. This is how we interact. And changing that can be painful, whether it is relationships and contracts between business units or between components. API change and versioning is something that should be taken very, very lightly, or it should not be taken very lightly. And so it's important to track these kind of contracts and track the dependencies and anticipate long adoption cycles, because at the end of the day, changing an API contract or changing a relationship between business units is going to take some time to actually change the processes and change the tooling that have all emerged to support those integration points. So I'm going to get down to the meat of it. This is a developer track. So we love our tools. So let's get into the tools. So in monoliths and microservices, you had really two different kind of tool forms for a lot of these common concerns. In monoliths, you had shared libraries. Everybody knows about dependency management. I don't need to belabor that. You also had maybe you were using direct libraries, or maybe you were actually generating code or weaving in common aspects. In microservice land, you actually end up using middleware, sidecar processes, and orchestrators. Middleware and sidecar processes feel a lot more like code weaving. They feel a lot more like aspect-oriented programming, because they're inserted into the middle of some call stack, right? They're not necessarily part of any of your services. There's something that communication between services go through, right? And so it allows us to weave these things together, much like aspect-oriented programming. In orchestrators, if you're here, you probably have some rough idea what an orchestrator is. So I'm not going to belabor that either. So the first big difference, right, in our shifting context, we had memory integration versus network communication, right? And so as soon as we go to the network, suddenly the main thing we have to worry about is that we didn't have to worry about before, is suddenly we have to create trustworthy communication, right? Before we had process memory isolation. We could say the operating system will make sure that no one's going to get in there and mess with our call stack, mess with our memory. You don't have that when it's distributed. You certainly don't have that when the communication is over the network. So we don't have simple function calls anymore. Now we have to worry about intercomponent authentication, authorization. You have to worry about encrypting the channel if you do care about confidentiality or any of the other security concerns. And you have to worry about maintaining that channel. Is the connection live? Can I continually make that call? Is it up? Is it down? Etc. The tools you're looking for in this space are service meshes, API gateways, or service client libraries like Netflix Hystrix. The nice thing is that they're there, right? And if back-end intercomponent communication trust is something that's important, you should genuinely look at one of those things. The next thing is distributed coordination. In a monolith, you had one process space. You had your set of threads. If you were doing concurrent programming, you could deal with this stuff locally. In a distributed system, you don't have any kind of like in-process singletons. You can't say whether or not something is only running once. You might be able to say whether or not something is running. That's a good first step. But being able to say that there is only one process running is a harder thing. And so you need things like distributed locking or leadership election. And the great news is you kind of have that provided today via tools like orchestrators, or you can DIY with storage backend that support locking or fencing. Even most orchestrators, at the end of the day, I think both Swarm and Kubernetes depend on etcd-like primitives that do fencing. So if you have some singletons, pick up one of those tools. The next thing, and this comes to wall clocks, the dependence on wall clocks. Linearizing log or event streams without clocks is a pretty challenging thing to do. You can certainly say that certain things happened in a specific sequence if you're only looking at events that were emitted from a single host. But once you try to start interlacing those with other hosts, if you just say, oh, we're just going to like sort by the timestamp column, you're going to run into all sorts of neat problems that are never really fun if you actually have a hard dependency on those things being linearized. And so this comes into like the whole log aggregation and centralization. You actually didn't really have that a whole lot of a problem with that in monolith stacks because generally speaking, you were writing on one process to one log or a very small number of processes to some very small number of logs. The good news is you've got all sorts of tools to help you deal with this. Tools that introduce causal clocks are neat. And that's, I think I'm going to touch on that a little bit later. But you have tools like ELK and FluentD and syslog that will kind of help in this space. Maybe not necessarily with the linearization or strict linearization, but definitely with the aggregation and centralization. Multi-process debugging. Debugging in a microservices environment can be very, very challenging because what do you attach your debugger to, right? My team, 300 services, forget it, right? Like any one request that came into our system spawned probably at a minimum 50 other child requests between other services. So you were kind of like, either I needed to be attached everywhere, which doesn't really scale for me, or I had to come up with some other way of dealing with it. And we didn't really have a better way of dealing with it at the time. The cool thing is now we can use these distributed tracing tools like Zipkin and Jaeger, and actually some of the service mesh suites have distributed tracing integrated as well, so you can actually see causal relationships between different requests in your system. This helps a lot with debugging. You mix that together with logging, and you can kind of infer a lot of those causal relationships between events. The next thing I want to talk about is the evolution of testability. So in monoliths, your tests were versioned with your code. We were testing consistent snapshots of your code, meaning I'm going to test this version of my software now, right? And you could test the whole thing kind of in isolation and against known state. You had unit functional integration testing. These were all fantastic things, and I'm sure you're all abusing all of those forms of testing today, right? But in monoliths, you had this kind of like loose contract between components. You could, if you really wanted to, code to interface, but you didn't really have to. But the nicest part about testing in a monolith is that if it was going to fail and your tests were going to discover it, it would happen before you publish your software, right? That doesn't happen in microservice land. The good news is you can use all of those exact same tools to do the exact same thing, just continuously and at runtime. One of the reasons is because in microservice land, there is no runtime consistency, meaning at any given moment, you might be running any n combinations of all of those specific pieces of software. They might interact in all sorts of different ways. So you need some kind of like continuous or edge integration testing. When I say edge, I mean testing when something changes. And for the most part, we know when we're deploying software, or even our orchestrators will help us determine, like, because they are deploying the software, when that's happening. We can detect the edges. So we might not necessarily need to be continuously testing, right? But at the very least, testing when there are changes. In contract validation, like validating our APIs, validating their APIs are behaving the way that we tell our consumers that they're behaving, really becomes critical. That's kind of your validating that our implementation meets a specific interface sort of assertions. And if you'd even just start with that in a microservice implementation or in a microservice architecture, you can get 90% of the value of testing out. And that's great. And a lot of times you can develop those tests and those test suites during development actually as a lead to real implementation. You can use those as you're validating that you're complete, your service is up and running, it behaves correctly. And those tests end up defining your service contracts. So the next one I want to talk about is dependency management. And so like names and versions identify contracts. This means like the API. This means the services. But it's not just the code. It's all of your interfaces, all of your data structures, and your data, which is one kind of often overlooked thing. Once a service that has state or has some state behind it starts to accept data into it, it becomes specialized, right? When I run my Superfund service in North America, and I start writing my North America client data into Superfund service, it becomes Superfund service North America. When I bring up my EU stack, and I start writing my EU customer data into that, that becomes Superfund service EU. Those two services are not equivalent. I could not call one or the other. Like the data they hold actually shapes the contract that they have with their clients, right? And so also you're taking on process versus code dependencies, which means you're forced to code to interface because you have to have this communication protocol. And you really need some kind of runtime dependency modeling. And I've looked and looked and looked, and in some closed ecosystems like service meshes, there's some way to declare what your service's dependencies are, your service dependencies are. Like maybe I have a fixed dependency on a database, or maybe I have a fixed dependency on DynamoDB, or maybe I have a fixed dependency on a FedEx API or something like that. But I haven't seen any way. Maybe someone in the crowd can help after the fact or after the session. I haven't seen any tools for actually modeling those things and tracking those things and accounting for them. So if I was to walk into an organization that has 300 microservices, and I sit down and I say, okay, show me like your service dependency graph, they wouldn't be able to do it, right? I could help them generate it by examining all 300 of their services. But even then, it might be challenging for them to say who depends on them, right, outside of that organization or out into their customer world. I've dealt with this problem very specifically. This is near and dear to my heart. I ran a deprecation campaign for 2 very legacy systems at Amazon, and like they have a tool to do this inside Amazon, but they didn't have it always. And these things were 10 years old. And so when I'm going to deprecate these services and retire them and turn them off, I need to go out and find everybody that's calling me and make sure that they know that this is happening. And it took us something like 9 months because only a quarter maybe of our clients were included in our dependency map. And it was a huge lift. So if we could find a tool out there for modeling this thing, it'd be great. So the last section I want to talk about are tools that help with the logistics problems that you're going to find when you go to service software at scale. The first one, artifact management. You only have one service. You only have one stack to publish, right? You can just SSH into the boxes that you're running it, upload your new jar, and do like a Maven deploy just locally. You can manually do that. It's not even that much work. It's a crappy process. It's not automated. It puts a human in the middle of it, which means that they might accidentally type like rm-rf/ accidentally. But it's manageable, right? Like it's concrete. We could have like a little wiki with a runbook that says, don't type that, just type Maven deploy. You can't do that in microservice land because you've got 1 billion hosts running 1 billion different versions of 1 million different services. And keeping all those things, all those versions straight is a nightmare, right? You need automation for this. You need some kind of tooling. At the very least, you can't just like be building artifacts on the fly, right? And just saying, well, I'll just upload the one that I just built on my laptop. So one of the first tools that Docker, one of the first reasons I loved Docker was that, even in May 2013 when I found it, I was able to identify specific versions of somebody else's software that I wanted to run, download it, and start it instantly, right? So one of my favorite parts, if you look at Docker in action, there's an entire chapter, like a chapter and a half, dedicated to Docker registry. I think it's one of the most important, most critical pieces of the entire thing, because it's all about artifact management. And then secondly, feeding those registries and taking artifacts out of those registries and put it into handing it off to your orchestrator, or any of your CI/CD pipeline tooling, right? That kind of stuff will really become necessary as you go into microservice land. I would almost say that it is a prerequisite. You should have an automation story down. Even if it's an early one, you should have something down before you really start jumping into this domain. But it's okay, like those tools exist, right? Like it might be one more thing you have to do, but it's a relatively low risk exercise. Controlling changes a lot with microservices. Where you had release engineering before, and you could say, oh, we're going to do a release this Friday. And everyone in the company would stop coding on Thursday or something like that. And your release engineers would be furiously merging stuff and prepping and doing builds. You can't do that anymore. You end up with this distributed change management processes, which ends up looking just more like processes and tools for communication. You also end up looking for declarative desired state. And like, people who know me and work with me frequently are really tired of hearing me say desired state. That comes out of my mouth constantly. It's all about desired state. What do I want the state of the system to look like? I'm just going to tell you and hand it off so that you can review it. You can version control that, and you can validate it. You can sniff test it. You can test it before we do it in production. All of those things. A declarative desired state becomes really important when you have several components in your system. And the great news is, you get this. You have, this is a short list. Orchestrators handle controlling change for you. Kubernetes does a really good job of recording events when changes do happen. In practice, you also should come up with like a team process for communicating changes. Like if I'm going to change my team's microservice, my team probably knows, but maybe my consumers need to know as well, right? They're not going to necessarily be pushing their code changes as well, but we need some way of clearly communicating that, because if something does happen, they need some way of being able to say, okay, what changed today at 5 p.m.? Why am I getting paged, right? And they need to be able to attribute that pain somewhere. The next thing, monitoring and health. Monitoring one service is pretty easy. Monitoring N services is a real labor. You need to come up with, for each service, how do you define health? There's all sorts of different ways to define health. It's really easy to go, oh, I'll just do an HTTP ping endpoint, but like, what does that even mean, right? And is that really health? Like, just because the ping endpoint's up, does that actually mean your service is healthy? The ping endpoint might be up, but the database behind the CRUD service might be down. So is that healthy? I don't know. So really you have to ask yourself on a case-by-case basis, what does it mean for this service to be healthy? You have to determine how often you need to test for health. You need to determine how many missing or out of threshold data points trigger alarms, because sometimes you have things healthy, not healthy, healthy, not healthy, healthy, not healthy, which might be a healthy state, probably not, but it's something you need to identify for yourself. And finally, what actions do you take on your monitoring health, right? Are you going to depend on your, spoiler alert, the tooling orchestrators to mitigate service health problems? A lot of times you can just do that, right? Other times, maybe you also additionally want visibility into those events, or maybe these are events that actually require operator integration, and so you need alarms, and you need, and so really, like, but then again, this is a solved problem. We've solved this several times. We've solved it at scale. Orchestrators help with this. You can use tools like Nagios, or you can use any of the million visibility and monitoring and alarming products and platforms that are out there today. They all work great. There are very, very few really negative anecdotes I have about any of them. So just pick one and go. They'll wine and dine you. It's fine. Just swing by the booth. The next big thing you have, and this is one of my favorite things to think about when you're dealing with microservices versus monoliths, is that monoliths integrate on memory addresses, microservices integrate on network addresses. What this means is you've got a build time versus runtime integration problem. You can't build your entire system like you do by compiling it and testing it all in one snapshot. Instead, we have to worry about doing all that integration work at runtime. At build time in monoliths, you can do fancy things like statically link your libraries. You can do even fancier things like use dynamic linking. Right? In microservices, it's runtime only, which means dynamic only. There's no such thing as static linking. Right? But what it also means is that we need a distributed linker so that we can link those dependencies. And the good news is we already have a few. Distributed linking. It's all about name to address resolution. And on a network, we generally call that service registration and discovery. So we do service registration and discovery a number of ways. You can go very low tech and use bootstrap addresses. This just looks like knowing what IP address the service is at all times. That certainly works, and in certain small environments, that's probably sufficient for a lot of teams. Going the next step more sophisticated, you can use a slow change service discovery mechanism like DNS. This is built into, pretty much every network-enabled system. So it's available. You can just use it. That covers like the other 90% of use cases. Sometimes, in addition to one of those, when you have a higher entropy system, like an orchestration platform, you have lots of deployments happening all the time, interesting rollout patterns, or you just have several endpoints providing one service, you end up using a virtual IP address or AKA load balancer, reverse proxy, something like that. And so these provide kind of like low entropy service discovery mechanisms like DNS, a bridge between that and high entropy environments like you'll see in orchestrated platforms with several replicas of service software running. Next, you've got native service discovery. I kind of call this out as separate because this means that like your code is coded to a specific proprietary service discovery mechanism. If your code is coded to like console, for example, it's doing its own service registration. That's a proprietary interface, at least for registration. Console also provides DNS discovery mechanism, which is nice. But it's still kind of a proprietary integration. Finally, you've got service meshes, which are, generally speaking, open frameworks. They work like woven sidecars. They're usually orchestrated alongside of your software. And all your software really needs to know is that it has a dependency named Bob service, and not much more beyond that. It just trusts that when it opens a connection to Bob's service, that there will be some aspect, some component that provides distributed linking and gets it to the right place. And in the case of service meshes, they also provide all those additional service architecture best practices like back off, retry, jitter, all that good stuff. So in closing, I just want you to remember that when you experience a new problem in microservices, every single one of those things that I talked about has a monolithic architecture equivalent. There's nothing new in there. Whether it's distributed linking or dependency management, these are all the same problems, right? And generally speaking, there's a new tool to solve those same problems in the new context. So there might be a lot to do, but there's fairly low risk if you look for the right tools and you go into it with eyes open on these problems. Before I go, remember to take the breakout session survey for me. I'm contractually obligated to ask you to vote for my session. I'm just kidding. And ciao. If anybody has any questions, we've got a couple minutes left. Thank you.